Sure. Okay. Well, welcome to the building part of BayThreat this year. I'll be your first speaker. This talk is entitled "What do you do when they're in your server room?" Originally, it was "What do you do when they're in your house?" But I think that as we'll see as the talk goes along, sorry, this is reflecting quite a bit. Is it good back there? I'm hearing a lot of echo. Yeah.
I think something is not right with them.
Okay. Can everybody, if I speak like this, can everybody, it's cutting in and out, I think. Right. If you can get just closer. Higher. Okay, I can just hold it, but it seems to be cutting in and out. This is all right. So this is what happens when you're the first speaker in a conference. Yeah. Okay, so I'll, I think, crane my neck down a little bit like this, and hopefully I'll be able to get things across. All right, so this talk is called White Box Cryptography. What do you do when they're in your server room? And just a little bit about me first. I've been doing security, crypto stuff for a while. Right now I work at a place called Cloudflare, which is a security and web performance company. What are you guys going to get out of this talk? What do I hope for you guys to come away with from this talk? Well, first, I would like you guys to, by the end, you should know what white box cryptography is, the very broadest strokes, and why it's important, or why we, meaning the security industry or the computer industry in general, need this now more than ever, and some key concepts for actually implementing white box cryptography. And along with that, there's going to be a small announcement at the end, so be prepared. This is just steps for the future. Right here? Okay. Yeah, sorry about all this. Hello, 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 hello. Hello? It's now mute. It's green. It's green. Okay. Well, I could maybe just project or use this.
This was actually an IQ test for our speakers.
I guess I failed that one. Hello, hello, hello. Okay, well, I'm just gonna press the button. I get it's green. Hello, green, orange. Okay, I don't have much time, so this is supposed to be a short talk. Let's talk about physical access. So this is something that other sessions are going to get into, but let's just think about having physical access to machines. What does that mean? If an attacker has access to your machine, then what people say in the security industry is it's over, right? That they have everything. Eventually, it only takes time. They'll get all your secrets on that machine. So some previous attacks, like cold boot attack for attacking full disk encryption, evil maid, we'll talk about that later in a different session. Even jailbreaking, you can consider having physical access to a machine and getting its secrets out as, have physical access. And the solution that some people say of, PCI compliance, some other things like that, just lock it up. I mean, we'll have other hardware type solutions for this right now, but if you think about it, just people say, lock up your computer, don't let anybody touch it. So it begs the question, what about servers? Where are modern web servers kept? Who here runs a website or a web service? A lot of people, right? Almost everybody in this room. Do you own your own data center? Is it hosted in a physically secure co-location facility? Or is it in a virtual machine somewhere in the cloud? What does physical security mean in that case, if you're hosting it in some machine that you don't know about? What about more of your content? Do you have stuff on a globally distributed CDN? Maybe. You might have some stuff there. And under which national jurisdiction do these computers live? Things to think about for physical security. You can't just take your server machines and put them in a box. I mean, you can, but sometimes you can't. So, I mean, server breaches, they happen. They happen. It's a fact. in our industry that server breaches, people getting in, breaking into systems, whether through physical access or other means, it happens. So how long does it take for someone to get your secrets once they've broken into your machine? Well, that really depends on the reverse engineering skill of the attacker, how long it takes, how familiar they are with your systems, what you've used, and it really is a diminishing cost. So every time that someone breaks into one of your systems, they, if they're a good hacker or a good reverse engineer, they'll have built tools specialized for what they broke into, or it'll be easier the next time to get the secrets out because they know your systems, they built things, etc. So wouldn't it be great if would it be interesting if there was a computational burden placed for every time someone wanted to get into your system to get a new secret? So, for example, this is why people use scrypt and decrypt for hashing passwords now. There's a computational cost, and this is sort of the same idea for Bitcoin, and you have to actually have a proof of work to show that, to get what you want out of things. Whereas if you just have a regular server, it's a matter of skill on the attacker. There's no computational proof. So if there was a burden placed on the attacker that you knew took a certain amount of time, you could potentially rotate your secrets in a way that you could prevent that, so that they would expire by the time that someone gets through it. So let's just talk a little bit about cryptography for a bit. So this is what we consider the standard model, or the old school model of cryptography. Is you have Alice and Bob, they're trying to communicate with each other, they're authenticating each other, they want to make sure that something gets through to the other person they know who they're talking to, and you have an attacker, this evil baby Eve, who's sitting on the line, modifying things, changing things, reading things, and the way that original crypto algorithms mathematically are designed is to prevent this kind of attack. And more recently, there's been more emphasis on something called the side channel attack. So if Eve has access to other streams of information from Alice's computer, such as timing, how long it takes to do the crypto, fault, injecting faults into it, or potentially how much power it uses, the power signals on Alice's computer, Eve can kind of figure out what the key is. And in crypto, the core thing that you're trying to, that makes it what it is having access to this key. Now, in the white box threat model, this was proposed. This is the strongest possible threat model. Eve is on Alice's computer, watching everything that Alice does, and you can kind of think of this as Eve is Ali. Eve is herself the opponent, and Eve is trying to get her own key in a way. This is the threat model that's the hardest possible thing to defend against, and that's kind of what white box cryptography is for. It's a cryptographic implementation that hides the key from everyone. So think about that for a second. It hides the key from attackers on the wire, classic attacks, attackers outside the house, your gray box side channel attacks, and attackers inside the house, the evil man, the person themselves can't get their key. And this is what it was designed for. And I'll just reiterate that point again. It's a protection against key extraction from someone they have an implementation of an algorithm that they can't get the key out, no matter what. So it secures keys, not data. And in an ideal white box implementation, an attacker is no better off than that baby sitting on the wire. And they have to do a brute force attack or some kind of mathematical attack to break it. To make this more concrete, here's one example in which this is used, which is digital rights management. If you guys ever use Spotify or Netflix or anything like that, the media that's coming down is encrypted, and your, as a machine or a viewing device, you get the decryption key. But content owners don't want you to have that key. They make sure that the consumption and decryption of this content happens in a very specific controlled way. So this is one perfect example for white box crypto. Is the attacker is the consumer. And so this slide has a lot of information, but basically the history of white box crypto is it was invented in 2002, and there's been a lot of academic attention. There's been a couple papers in the recent years that have been breaking previous ones, and it's really a work in progress academically. There are some relatively strong white boxes, none perfect, and there's no proof that you can take a known cipher that we have and make a perfect white box, but there are examples of strong white boxes, ones that have a strong computational burden. So now that we know what this concept is of white box cryptography, what does it get you as a user, as an owner of a system, or as a developer? Well, attackers cannot transform the key into a known form. That's what it gets you. So if someone wants to use your key to decrypt some secrets or to do something or other, they have to lift your code or leverage your specific code to do so. And this prevents something called the OR attack. And OR stands for break once, run anywhere. And you can imagine if you steal a key from somewhere, you can write your own cryptographic toolkit that uses standard libraries, OpenSSL or whatever, and to decrypt stuff and call it with it. Or even specialized cryptographic hardware to do so. And you can imagine that if someone were to scoop up all the data encrypted on SSL on the internet and manage to have those keys, they could run it through a really fast processor and decrypt it. So having a white box key or a white box implementation would prevent this. And what it also gives you is you can represent your keys in different ways, or different places that you send them. So if you discover that someone has found one of your keys, or you discover that someone has lifted one of your keys or one of your algorithms, you know who it is. You can fingerprint it and have to do something called traitor tracing. You can track who it is, who finds it. And because it's so hard to break a white box key and get back to the original key, you can rotate your secrets on a fixed schedule, as I kind of mentioned before. So let's think about which algorithms you would want to do this with. Well, there's symmetric key and public key crypto. And for symmetric key, people don't really use DS anymore. The triple DES is still used, but these are AES, DES would be ideal. RSA and ECC, these would be sort of good targets for doing having a white box implementation. And right now in academia, there's AES and DES are the only ones that have been published, but there could be implementations for RSA and ECC. So let's have a thought experiment now. Let's see how we could do an implementation of 120-bit AES such that it's a white box implementation, such that someone could not extract the key from it. Well, what is a cipher? It's really, you have an input and an output and a key. And you have a very simple script of mathematical operations that you go through to get from one to the other. Well, you can if you think back to like classical cryptography, you can have something called a shift cipher, which would be the description of the cipher would be take whatever letter you are at and move it up by 2. That's the simplest explanation. But at the same point, you could also say have a lookup table or a map, basically that would say for each letter in, which letter out is it? And mathematically, that gives you the least amount of information about the structure of the algorithm. A lookup table is really just a map. It's a one-to-one map. And in theory, a perfect white box implementation of AES would be just that, a lookup table. For every input for your 16-byte block that you want to encrypt, it would be mapped to a specific output. And that would be the description of the algorithm. And you really couldn't reverse it because that's the kind of thing that cryptography is safe against. It's known to be safe against. If you have an oracle to look up inputs and outputs, you can't find what to do. So in theory, that's kind of the ideal case, but in practice it doesn't work. I mean, you have to have 2 to the 27 terabytes of data for one AES key. So it's a little bit overwhelming.
I know this place is not made.
Well, let's think more closely. Let's look at AES in a more granular way. There are 4 basic steps to AES. Subbyte, which is a byte-wise substitution. Shift rows, which is like a little permutation of your bytes. it's constant. Mixed columns is, it's basically a linear combination of what bytes you have. And add round keys is when you actually XOR in the key or a piece of the key schedule into your algorithm. So these are all very small, simple things. If you look at it as kind of a circuit diagram, this bytes, this is a lookup table. And each one of those XORs, it's really on a byte-for-byte basis, can be replaced with the lookup table that represents that XOR. And that's really 256 bytes long. That's it. So, okay. Yeah, and you can imagine you can swap the place of shift rows and add round keys and combine this step with that step and get a bunch of little lookup tables. And if you have one lookup table after another, you can combine them into one with the same information just by following the path, I guess. So just broad strokes, add round key subbytes, all these kind of steps can be turned into lookup tables. And that really doesn't get you that much, because if you look at a lookup table, you can figure out what it means, right? I mean, if you know that it represents an XOR, it looks like an XOR. What makes white box cryptography implementations, as they are, really really work is the fact that you can compose these functions this way. So say you have 3 lookup tables, F, G, and H, and you have 2 random lookup tables, R and Q. You can take R and F and merge them together into F prime. Take these and merge them into there, and this and merge them into there. Each one of these lookup tables is going to look random, and that's basically it. That's the core of white box crypto. Is your representation of all the different steps are random looking lookup tables, and you have to work your way from the back, from either side to the middle to figure it out. And well, there's this idea of a white box compiler. You just get a description, and it gives you an implementation. And compared to regular crypto, it's like the keys are bigger, cost more for memory, performance is slower, it's harder to integrate, but you do get all those things that I mentioned: trader tracing, everything else. And right now in the industry, it's mostly licensed or DRM, and that's money, 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 right? And but there have been practical breaks. There's Frac magazine published a pretty interesting break of an academic crypto one recently. But there's no commercial grade open source. And right now, if people want to use white box cryptography, there's no portable solution. There's no way to do that. So what I'm doing here is I'm introducing open white box. This is a group of individuals that are going to work together to actually have an open source implementation of white box for people. So if you want to participate in this, come talk to me. There's a Twitter handle, Open White Box. This is the first announcement of this project, and it's kind of in its infancy. And hopefully, what we can do is take the best academic proposals and make an open source version of it for people to use. And yeah, that's it. That's the whole talk. So we've got another minute and a half of questions. So this is the evil mage. She's very sad. Yes.
What's your envisioned threat model for this? Like, what problem are you solving? Would this be, or I can imagine one you can tell me is this a solution? So in the case of like law enforcement malware, you're under surveillance, your system is under surveillance, the surveillance agency is on your computer, but you still want to have secure communications. Would that be an application?
Yeah, so the question is, if, say, you have a piece of malware run by somebody who wants to read your keys on your system, is that the use case for white box crypto? And it definitely would, because if you have somebody on your machine looking at what you're doing and extracting your keys, they don't have the mechanism to actually use those keys. And if they do, you can trace it back to your specific implementation. And it's a real headache for law enforcement agencies or anybody else to reverse engineer custom crypto algorithms and use specialized things for each person at a time. It's a matter of scale from that perspective. Any other questions?
You mentioned automatic rotations. How does that happen?
Yeah, so you could think of, say that you have your SSL private key, and rather than using a regular implementation of your straight up SSL private key, you have a white box version of the SSL private key. And you set your expiration date for your key to 2 weeks. And so if you rotate your SSL key every 2 weeks and you know that it takes more than 2 weeks to break the white box, then you know that someone can't forge your something. So that would be one specific implementation of this. And we're down to the end. And yeah, that's it. Thanks very much. And enjoy BayThreat.
Test. Hey, how is that working?